I'd like to show you how to do problem number 47 here. 47 describes an arrangement of charges here, a 2 nanocoulomb, minus 6 nanocoulombs, and a 2 nanocoulombs. And they want you to find the net force these three charges represent onto this 1 nanocoulomb charge right here. And it asks you to write the answer in component form, which is the x hat, y hat, j hat, or, excuse me, x hat, y hat, z hat, or I hat, j hat, k hat notation. So let's see what we can do here. The 2 nanocoulomb force here obviously pushes on the 1 nanocoulomb because like charges repel, so the 2 nanocoulomb here is going to have a big force vector going this way. And we'll label this vector here F2 left because it's the 2 nanocoulomb charge on the left presenting that force. This one will do the same sort of push, so it'll sort of push this way like that. This will be an F2 right, 2 nanocoulomb force due to the 2 nanocoulomb charge on the right. Since this is an oppositely charged charge relative to the 1 nanocoulomb, it's negative versus positive right here, this will definitely pull on the 1 nanocoulomb charge, something like this. So I will just sort of draw this force vector going way up here, but for the sake of working down on the 1 nanocoulomb charge, I will label this arrow right in here that I've drawn here F due to the 6 nanocoulomb charge, and you can put a minus sign in the subscript if you want. So I've identified then 3 forces on the 1 nanocoulomb charge, this one, and this one. Now the job just becomes to find the net force that these forces present. So I can sum the forces in the x direction, and that'll be sort of my Fx here. And you can also sum the forces along the y direction. That'll be my Fy, just like you did in Physics 141. So let's just sort of keep at that. What I can do next then is start to identify vector components that exist here. So for instance here, for this F2R here, it definitely has an x component this way and a y component down like that. So I can label this side over here, say F2 right y, and label this F2 right x for the x and y components of F2R here. And I can do the same thing for this force over here. I'll label this F2 left x, and this one right here, F2 left x, excuse me, F2 left y. So I have the 2 components on there. I need the components because I need to fill only components into these sum problem, these force superposition equations right here. The force due to the minus 6 nanocoulomb charge is already along the y-axis, so I don't have to do any vector decomposition of that because it already points up along the y-axis there, so we'll just leave it like that. I will need a couple of angles in here to use sine and cosine to find the vector components here, and it looks like if this is 45 degrees here and this is a 90-degree angle, this will be 45, and since there's another 90-degree angle down here, this will be 45 degrees down here. This will also be 45 degrees in here. So now I have right triangles and angles, and I think I'm in pretty good shape to find the x and y components here. So if I sum all the x forces on this 1 nanocoulomb charge, what I'll get here is I'll get a minus F2 right times the cosine of 45 degrees. That finds this component right here based on this magnitude of F2 right here. And I put a minus sign in here not because of any charge considerations, but because it's pointing over to the left, and we like to call left negative in this class. And I also have another force here, which will be an F2 left times the cosine of 45 degrees, which is this x component of the other force due to the left 2 nanocoulomb charge pointing this way. And I have a positive sign in there, again, not because of any charges, but because it points to the right. And there you go. A left versus pointing x component, a right versus pointing x component. I have the full magnitude in there. And this equation right in here, because there are no other x-directed forces on the charge, gives me the net force in the x direction on the 1 nanocoulomb charge. I can do the same thing along the y-axis now. In particular, now I'll work in the 6 nanocoulomb force, so that sort of points up, so I'll call that plus F6. That refers to this green arrow right here. Then I have 2 downwards pointing y components right here. Namely, I have a minus F2 right times the sine of 45 and another F2 left times the sine of 45. This force right here describes this downwards component here, negative because it's pointing downwards here. F2 left y over here is found from F2 left sine 45, so this term right here refers to this downwards component right in there. These are all the y-directed forces on the charge, so I can put a big box around these as well. Okay? Now what we have a bunch of equations, and we have our angles all set up, and things are looking good, but now we need some magnitudes of these forces. What is the magnitude of F2 right and F2 left and F6? Those come from Coulomb's law. So I can write that F2 right, for instance, here is going to come from K, our electric constant that we have floating around in the class, times the 1 nanocoulomb charge, 1 times 10 to the minus 9 coulombs. And the other charge in question now is going to be the right 2 nanocoulomb charge. We're talking about this force right in here. So I'll put a 2 times 10 to the minus 9 coulombs in there. and then of course I'll divide by the distance in there. It looks like they're 5 centimeters apart, so 5 times 10 to the minus 2 meters squared. If you put this in your calculator, you will find the magnitude of F2R. F2 left comes similarly. F2 left comes from K, 1 times 10 to the minus 9 coulombs. There's also 2 nanocoulomb charge there, 2 times 10 to the minus 9. All that's going to be divided by its distance, which is the same as this one. There's a lot of symmetry in the problem, a lot of similar numbers. Doesn't always have to be that way. 2 meters squared. Put this in your calculator. That'll give you F2L. So these numbers and these numbers here can be plugged into there and there and there and there, because that's where the magnitudes are called for. And also you'll note I put only absolute values into all of these numbers here because I don't want the Coulomb's law calculation generating another minus sign, which would mess up my directions that I've already carefully placed into my sum of force equation right there. Lastly, the last magnitude we'll need is the force due to the 6 nanocoulomb charge sitting right there. A last application of Coulomb's law here. I can get F6 to be K, 1 times 10 to the minus 9. Again, the target charge is always that 1 nanocoulomb charge here, times the 6 times 10 to the minus 9 coulombs over that distance there, which I believe comes from a bit of a right triangle geometry in here. No, it's not even a right triangle. All the charges here are on a circle like this. So if this is 5 centimeters, this is also 5 centimeters away. So 5 times 10 to the minus 2 meters, that quantity scored in there. So if you do all these calculations here, standard calculator or in Sage Math or something, you can get all these magnitudes of all these forces here. You can take all of these numbers, plug it into your sum of force equation up here, and you'll have Fx and Xy. In the component form, which is the way the problem wants you to report the answer, you can get that now by writing the net force vector. Net force vector there. Whatever you get for your Fx up here, you can write Fx I hat plus Fy j hat. And again, these will be the actual numbers that you got when you calculated your forces in these two equations up here, and this is the way you report your final answer. And the answer that I got for this anyway is that the net force here is going to be something like 1.02 times 10 to the minus 5 I hat plus 2.16 times 10 to the minus 5 j hat. And that's the final answer that I got for this one.